Pleasure to be here in my old kind of place, working place here in Mainz, to tell you a little bit about our efforts on many-body localization. But actually, this being a SPIN conference, I actually thought I'll start with a different topic, actually, which is also interesting, I think, for the community here, is on so-called Rydberg-dressed quantum spin Ising chains and our efforts to generate long-range interacting spin chains with ultracold atoms. So let me start with that topic, and then I'll move on to the new stuff on MBL. And so just to give a brief motivation why this is interesting, you know, many of us in our field are trying to engineer long-range interacting particles. On the one hand, the ion traps do this very well. Then we have now magnetic atoms or dipolar molecules. But I think the even stronger interaction strength can be achieved with Rydberg gases, which have been catching up a lot very recently. And I'd like to show you our latest progress on that in generating long-range interacting spin chains. So here's the basic idea, if you've never heard about these Rydberg atoms and how you generate spin-spin interactions from them. So basically, Rydberg atoms are very highly excited atoms. And when you try to bring two of them very close to each other, two of these very highly excited atoms, you have an enormous shift of the energy between those two states. So there's enormous interaction energy, which can be on the order of several hundred gigahertz at the range of 1 micrometer between the particles. So that's really a huge interaction energy. And this has given rise to the so-called Rydberg blockade effect that people have made use of. We've also looked into this. You can show, for example, that you get crystallized spins in 2 dimensions, for example, when you turn on this very strong Rydberg interaction. Now, it's so strong that it's actually too strong. So we actually want to make it a little bit weaker and a little bit more controllable, that we can use it to have more highly controllable spin-spin interactions in the system. And this is where the Rydberg dressing idea comes into play. So imagine now you have your ground state atom, and then you have your Rydberg state. And now imagine you tune a laser, a single photon laser, off resonantly to that Rydberg transition. So this will mean, like in a dress state picture, that out of this G atom, which can be a stable hyperfine ground state, for example, of our rubidium atoms, you make a G tilde atom, a dress state, which is mostly the original ground state, plus a little bit of a mixture of the Rydberg state. And of course, here delta is larger than omega, so that mixture is really just on the level of 1%. So we just admixed on the level of 1% of this Rydberg atom to the ground state. Thereby, of course, we kind of don't get this full interaction strength, but we don't want that. But we make things a little bit more controllable, and we make these objects actually quite long-lived, as you will see. So what happens? So if you just have these 2 atoms approaching each other, this would be 2 ground state atoms, ground state Rydberg and Rydberg. You have these potential energy curves. When you turn on the light, you to first order get a AC Stark effect, just a light shift. So these energy levels of the ground state atom will shift from the state without light by a large amount. That's not what we want. That's uninteresting. That's what makes dipole traps, optical lattices, and so forth. But then again, to second order, if you go to second order in the coupling strength, then you find actually this spatially dependent potential. And this is precisely the potential we want to have. So this is the long-range interacting potential we generate over a few micrometer distance with a strength of the order of about 10 to 15 kilohertz for the dressing, the interactions that we implement in our system. So this gives rise actually to a very peculiar kind of interaction potential. It's this so-called soft core interaction potential, which saturates here at some large value and then decays like 1 over r to the 6 van der Waals type to longer distances in the system. So if you now add to that, let's say, dressing to a state which is not spherically symmetric, for example, a p state, then you can gain a lot of also kind of angular dependence. You get a lot more flexibility. So with this kind of tunability in the system, many people in theory works have shown that you can generate very interesting interaction potentials which peak at some point, which have an angular, spatial angular dependence, have a lot of tunability with it, and also can, of course, be turned simply on and off whenever you want. So now let's see what, from a many-body point of view, what we get from that if we turn that on. So basically, if we now have 2 ground states, one of them we dress to the Rydberg state, and one of them will acquire this long-range interaction, the other one will just stay what it is, then we can couple those 2 states with a microwave field, and then we've generated a long-range quantum Ising chain. So you have this SX term, which is just the coupling between the 2 spins, and then you have this long-range soft core van der Waals potential due to the Rydberg dressed interaction in the system. And now you want to show that you have a coherent long-range interaction in the system. And in order to show that, you can do different types of experiments. On the one hand, you can use spin correlation Ramsey-type probes to measure directly the interaction potential. So these are direct measurements of the interaction potential of the spin-spin interactions, of this soft core potential in the case of where we had symmetric interactions in the plane or where we had asymmetric interactions in the plane. Or you can go to a different experiment, which I would like to show you now, where you basically really look for the collapse and revival dynamics of the many-body system. This is kind of some of the most stringent tests you can make to probe for coherent evolution in a many-body system. So what's the idea of that? The idea is basically you bring the system into a superposition of many eigenstates, and then, of course, you will have a dynamical evolution of the system, and this will lead typically to collapse and revivals of the dynamics of the initial state in the system. So this has been shown for kind of several examples for coherent state dynamics, for example, in Serge Haroche experiments of a single atom coupled to a coherent kind of cavity field. You can see that we've done that in the collapse and revival experiments on superfluid Mott transition. All these are kind of simple collapse and revival dynamics because there's typically only kind of one frequency component in these problems that is relevant for the dynamical evolution of the system. Now we can do the same thing with our long-range interacting Ising chain. We put all of the spins into the horizontal plane. Remember, we have an SZ interaction, and then we look for the evolution of the SY magnetization as a function of time in the presence of this kind of interaction potential that we have in the system. And what you can see from the theory plot here is that you expect actually a quite complex collapse and revival structure of the magnetization in the system due to the different frequencies that occur in the spectrum. So if you would just have a standard Ising chain with next neighbor interaction, you would have these orange lines. You see it's a very simple spectrum. If you have these long-range interactions, all the degeneracies are lifted in this Ising chain, and you get this much more complex spectrum in the system with a much more complex dynamical evolution, of course, of the many-body system in the end. So here's the data of the experiment that shows actually that we do see these kind of evolutions of the SY magnetization, these collapse and revivals. Remember, if it would just be decoherence, you would just end up at this 50% line and just stay there when the spins would simply decohere in the system. But we see even up to kind of long evolution times, we see signatures of this revival dynamics occurring in the system. And now we want to understand a little bit better where do these kind of revivals come from? Where does these oscillations come from that we see here? So we see typically something happening around 1 over u, where u is the maximum interaction strength we have in the dipole-dipole interaction. This is about this 13 kilohertz strength. Then we typically see something around 2u and something around 5u. And the question is, can we understand how this dynamics occurs and why there are these special frequencies that play a role? So first of all, when you put all the spins onto the horizontal plane, then of course you expect all kind of many-body states, all kind of spin configurations to contribute, and all kind of possible spin up and down configurations to be present in the system. And if you look at a beating of all those frequencies, you expect all the frequency differences between those many-body eigenstates to also contribute. So you'd actually expect for this very complex spectrum, you expect tremendous amount of differences in the frequencies to occur to give rise to a very complex kind of time evolution. Luckily, we only select a few of those through these matrix elements. Okay, so this matrix element tells us which of those frequency differences are going to contribute in our experiment a lot when we read out the SY dynamics. So in our case, what you can see actually, if you look at the interaction potential, we see we have this maximum interaction strength. This is this revivals occurring at u or integer multiples of u. And then we have, at the larger distances, we have this 1/5 of the interaction strength and something like 5% of the interaction strength of the original strength u0 occurring for larger distances. And especially this next neighbor and next neighbor interactions give rise to the interaction dynamics that I've shown you in experiments. So this 1/5, the revival at 5u, is exactly this 1/5 of the long-range interaction that occurs in this long-range interacting spin chain. Actually, I should also say the 1/2, this revival at 2 over u, this is actually mostly due to a boundary effect of the system. So at the boundary, remember, there's just a spin interacting with a spin to the left or to the right of it, not to the left and the right. So the interaction energy is actually halved in that case, which gives rise to this kind of peak here at 2u that we see due to this boundary effect in the system. Just to look a little bit how the entanglement dynamics occurs in the system, you can ask how do next neighbor or next neighbor spins get entangled as a function over time. You see actually that the next neighbor spins precisely get entangled at this very short time scale of 1 over u, and 5 times later you see that these next neighbor spins get entangled. And this is something you wouldn't expect in a standard icing chain. So this thing, only next neighbor spins becoming entangled. This is something for the icing chain that you would have, but this next neighbor spins becoming entangled in our system. This is really something unique to these very long-range interactions in the system. And I should emphasize that here the correlations kind of build up without propagating quasi-particles, quite different to the typical light cone dynamics that one has kind of with quasi-particles. Okay, let me just summarize the first part of my talk. So we've shown that we can see these long-range interactions, can generate coherent long-range interactions using Rydberg dressing. Right now, we can see this up to 10 times of the interaction time, which is rather long. If you compare it actually to ion trap experiments in Chris Monroe's group, they typically go out to 3 or 4 interaction times. Yeah, so this is not bad at all for a first try with cold atoms compared to the ion trap experiments. And we believe we have a lot of potential actually to increase the coherence time even further and also go to two-dimensional systems, to go to itinerant systems where you have motional magnets. So there's a lot of room to extend this to very exciting settings, but this is right now where things stand on these long-range interacting spin systems.
Excuse me, what's the current limitation on number of particles that you can get in a chain?
So right now, I think, well, right now in the chain is just basically size of the system, but we could go to, this was done with around 10 to 15 particles in a chain, but in principle, you could go also to longer systems, or you could go to two stripes, to ladder systems. I think this is natural extensions where you would really be looking also at new systems compared to the one-dimensional systems in ion traps, absolutely. And also, of course, you know, as you know very well, this is a very good setting also to look for these time crystals in also high dimensions. Yeah. All right, let me move on to the many-body localization topic and actually try to come back to two important questions that Netanel also raised in his talk. One, do we have evidence for MBL in 2 dimensions? And I think another hot topic in MBL physics right now is MBL stable when you couple it to thermal baths? Now, I don't know how familiar you are with many-body localization, but the basic idea is that we're looking for a localization phenomena where kind of quantum information persists for indefinite amount of times because you are generating a non-thermal state where kind of statistical physics fails completely. Yeah? So this, of course, can only happen when you're looking at isolated quantum systems. Whenever you couple a system to a thermal reservoir, you will always thermalize to the temperature of that reservoir, and you can never observe those phenomena. So it's a prime setting for cold atoms, ions, and V-centers or whatnot, where you can look at these kind of very isolated quantum systems. But the question still remains, said if you couple to a big thermal reservoir, for sure MBL will be killed. But if you couple to a finite reservoir, finite thermal reservoir, can MBL survive? And there's been a lot of arguments going back and forth in the community about this. So we thought, well, let's do an experiment. And I'll tell you our first output of this experiment. Okay, I don't want to go through the explanation of MBL, rather than just saying there are basically 3 ingredients that we today understand we need to generate these localized states. We need disorder, we need interactions, and we're looking at high energy density phenomena. And I think a modern way to understand MBL is, of course, based on this picture by Imbri, that we have kind of an emergent integrability model coming from the original Hamiltonian. So if you start with this original Hamiltonian with a disordered spin chain, you can effectively map it to a kind of integrable Hamiltonian in the end. And this kind of emergent integrability assures the stability of the system. So it will automatically run into this phase. It's not fine-tuned. It's not kind of depends on details of the coupling. You will always end up in such a type of Hamiltonian in the system. All right, so the first thing I want to actually look at, I want to just briefly look at actually dynamics at this MBL transition in 1D on the thermal side, on the ergodic side of the system. But before I do that, I just have to briefly explain to you the setting, which was our original setting for the observation of many-body localization, and that was work with Ehud Altman, Ronan Fosk, and Mark Fisher as team. And the idea, what we look at in general, a lot of the data you will see looks at the following settings. So we have a one-dimensional system. We have a Fermi-Hubbard model with 2 spin components in there. We can tune the interactions between the 2 spins, so we can always compare the non-interacting case to the interacting case. And then we start to set up a non-equilibrium state and look at the time evolution of this non-equilibrium state. And if there's some memory, even after a long time evolution, if there's evidence that this state remains stable after a long time evolution, then it cannot be a thermal state, because a thermal state has no memory about the initial state it was in, right? The thermal density matrix has no information whatsoever about the initial state. So that's what we look for in the experiment, and in this kind of setting that we had, this charge density wave, we just look at this imbalance parameter, which is just the visibility basically of this charge density wave. So we start with populating only even sites versus odd sites, and we look at the evolution of this. All right. So let's go now to the relaxation dynamics on the thermal side and look what we can expect there. And there was a very nice paper from Fabian Allé's group and David Luiz, who actually showed in these random spin chain models that I showed you before, what you actually see on the ergodic side, on the thermal side, as you approach the MBL transition, is that you see that this imbalance, which you can also measure for the spin chain, shows power law decay with an exponent of this power law that goes to 0 as a function of the disorder strength in the system. Now what's interesting when they were kind of plotting this data is that they find complete agreement where this power law goes to 0 with other measures where you have identified the ergodic to MBL phase transition. So typically in these mid-gap states here, you find around 3.5 for the disorder strength, you find the transition from the ergodic to the MBL phase. And looking at the relaxation dynamics, you find exactly the same kind of dynamical evolution. You see this going to 0 precisely at that point of 3.5. So this seems to be a good way of identifying the transition, apart from understanding, of course, the interesting physics at the ergodic part in the system. So we did the experiment then for our kind of one-dimensional Fermi-Hubbard model with a disorder in the system, or I should not say disorder, it's quasi-periodic potential, because people now, I think, understand there's actually a big difference between true disorder and quasi-periodic potentials. So this was with quasi-periodic potentials. So here's the disorder strength in the system, and we are basically trying to probe what is the relaxation dynamics of the system on this side. Okay. Now what people have found in the data I showed you before is that if you have true disorder, then basically you can think about this slow relaxation dynamics occurring from very rare regions in the system, where you have disorder, for example, already generating a localized phase where the disorder is larger than a critical disorder strength over some range, and this creates a block where you basically cannot thermalize through. So locally, over a very large scale, probably, you can already be in a localized phase, and through this localized phase, you have a very hard time of thermalizing the system. And then you can just estimate what is the probability of having such kind of rare regions, such Griffiths-type regions of length L in your system, and this would then give rise to an exponentially long thermalization time through these kind of rare regions. And if you calculate then what that means for the imbalance that we are measuring in the experiment, this basically measures the rare regions that have not thermalized yet at time t. This would directly explain you that you should expect these power law decays also in the experiment. Now there's an important difference, problem or difference in the experiment is that we don't have basically a true disorder potential. We have the quasi-periodic potential. And in quasi-periodic potentials, we know that this argument does not hold. There are no rare regions in the potential. Let me just show you this. This is true randomness. This is quasi-periodic in 2D. Totally different things. Okay? What do I mean by true random? Well, there will be regions where you find, for example, here a lot of these disorder values having the same value. Or you can find a lot of them having high values or between adjacent side differences. Whereas in quasi-periodic potentials, you do not have that. But what you can have in quasi-periodic potentials, due to the way how we load the spins into the lattice, we basically load them completely randomly into the lattice. We don't start with an antiferromagnetic order or anything. So you can have just from the initial state that you load, you could have a configuration where you have, for example, a lot of spin ups sitting next to each other. And if you have a lot of spin ups sitting next to each other, these are like non-interacting particles, you don't thermalize, again, you have an insulating block. Now, but that means, of course, this block is not static like this block, because this block can dissolve as a function of time. It's not static in the potential, it's just static initially in the loading, and dynamically it can evolve in the system. So we only expect these power laws over intermediate timescales in the experiment. So we did that, and we indeed find that if we plot the imbalance as a function of time, that there seems to be preference towards power law decays versus exponential decays, although I have to admit it would be nicer to have a larger dynamical range both on the y-axis and the x-axis, and we're working towards that. But if we just go ahead with this analysis and fit our data with this power law decays and look at where this power law exponent goes to 0, we can indeed find that the transition point is probably around 3 to 4 for this Fermi-Hubbard model system in the dynamical evolution. Finally, what I would like to show you now, the 2D data. And 2D is dramatically different from 1D. I mean, there's a huge region between the non-interacting problem and the interacting problem where the two systems behave completely different. So here I'm plotting the imbalance as a function of time for a non-interacting system for a disorder strength of 5J. Remember, in the Aubry-André model, the quasi-periodic potential, at a disorder strength of 2J, you have a transition to an Anderson insulator. So for non-interacting particles, at 2J, everything is localized. So for 5J, for the non-interacting particles, we're deeply localized already. Okay? Now, if we add just a little bit of interactions, 5J, you see that the interacting system decays completely. So it's not at all in an insulating phase at all. So there's a dramatic difference between the non-interacting case and the interacting case that we see in the system. And we need to go to much larger disorder strengths to actually localize the system. How large? Well, we can do the same analysis. This is now the 2D data where we plot the decay kind of exponent in the 2D system as a function of disorder strength. And we see here we would kind of have evidence for an MBL transition in these 2D quasi-periodic potentials at a transition strength of 9, at least 9 delta over J in the system compared to the 3 or 4 delta over J in the 1D system. Yeah, it's a little bit different fit function. It's this t to the minus z times log t correction in there. So that's in there. Yes?
So you were saying that it should saturate to 0, right?
It should go to 0. You're completely right. But there's always in the experiment, there is some residual coupling to the background, okay, to some background, to the environment. Okay, even our cold atom experiments are not isolated totally from the world. And there's always some background value we go to. Of course, we try to push this down, and that's why I can only say right now, if there is an MBL transition, it probably is larger values than 9, delta over J9. It gives a minimum value on the disorder strength. What we don't know, actually, we can measure this intrinsic lifetime of the system, but we don't know how to disentangle the decay from the MBL, the relaxation dynamics in the MBL phase, from the relaxation dynamics through the coupling to the outside world. We don't know how these two, what is the functional form in the rate that we measure. We don't know that. I think nobody knows that. Yes?
So what is the 2D quasi-periodic model that you're working with?
What it is?
What is the 2D quasi-periodic model?
So it's just two-dimensional lattice, square lattice, with independent quasi-periodic potentials along the x and y direction.
Okay. So, but
these are just a cosine beta x modulation where this beta is some irrational number of the lattice periodicity.
But this is just again 1D decoupled in two directions, right? In some sense.
Yeah, well, but the interacting system, yes. Well, this is why for the non-interacting system, you're right. It's like decoupled into two axes. This is why the transition for the non-interacting system happens precisely like where the 1D problem is at delta equal 2J. At delta equal 2J, the 2D system localizes for non-interacting particles. What this shows that if you add interactions, the system is not at all localized, even in a regime where the non-interacting system is deeply localized. Okay? Yes?
Perhaps in addition to that question, would you expect more localization if your quasi-periodic potential is at an angle with respect to your...
Yeah, that's a good question. We're looking into that. Yeah, it's not, yeah, there are some arguments for that, yes. So we're looking into that, what happens if you have quasi-periodicity along the diagonal direction, for example. Yes? Yeah. Yeah. All right, so let me come to the last point I want to make. If I have, do I have some? Okay, great. Is this 2D setting, true random potential in 2D and coupling to finite thermal mass. So this is done in a totally different experiment like the one before. This is done with rubidium atoms in our quantum gas microscope experiment, where we actually use kind of these digital mirror devices to project true random potentials onto the atoms. So we take these digital mirror devices, we project a disorder light pattern onto the atoms, and we actually can characterize this disorder pattern very nicely in the experiment because we can locally, at each lattice site, measure how much is the energy shifted of that lattice site. So because we have this high spatial resolution, we can really go into the system and measure So for example, this is the measured, spectroscopically measured map of the energy shift per lattice site. This is what we calculate, what we expect it to be, and you actually see that it agrees rather nicely. So you have this blob, this line is this line here, this ring here is this ring here. So, but you actually see we can really measure this side by side, and we use this measured disorder distribution, and this is what it is. So this is a probability of having a certain disorder strength of a lattice site. It's short-range disorder with a correlation length of about 0.7 lattice sites. So this is what we can give to you as a theorist, and then you can analyze what we see in the experiment. So the experiment we did there, 2 experiments I want to show, slightly different experiments, but the same idea again with this imbalance, slightly different this time. We make a domain wall in a mod insulator, and we let this domain wall evolve in the presence of disorder or in the presence of no disorder. And if it evolves into kind of a thermal state, we assume that there's no memory for the initial system, so it will spread out completely in the trap. If it evolves in a disordered state into an MBL phase, then even for long times we expect there to be kind of memory of this initial state and this domain wall boundary to be present in the system. And so now we can plot how many particles are to the right of this domain wall minus the particles to the left divided by the total number of particles. This is again the imbalance now for this domain wall, which characterizes whether it's thermal or non-thermal. 0 would be thermal, non-0 would be non-thermal. And you see as we increase the disorder strength, there seems to be a rather sharp point here where we cross over from this ergodic to an MBL phase, potential MBL phase in the 2D system with true disorder. Maybe what's even more interesting, if you look at what occurs for the domain wall, if you look at the density profiles of this domain wall, in the region it evolves into, you see that it has these exponential decay profiles. So this is a log plot. And from that we can extract a decay length. And this decay length actually diverges at a disorder strength, which is again precisely where this kink occurs for the imbalance data. Okay? So there seems to be a real phase transition here around this disorder strength 5 to 6 delta over J in the system. And remember the Anderson case, the non-interacting particles, they would have kind of this, you would localize the particles for arbitrary weak disorder. So there would be this divergent at 0. So it's a completely different behavior again than what we've seen for the Anderson insulator. Just to show you, here's the simulated data for the non-interacting problem from Vedika Kemani and David Hughes, because we don't have a Feshbach resonance in rubidium to do that experiment nicely. But you see, the non-interacting data precisely does what you expect. So for arbitrary weak disorder, you localize the particles and you get a finite imbalance. Whereas our experimental data, which is shown here, the light blue data, this is the one I showed you, is completely different behavior, localization behavior at a finite disorder strength. What is nice also is that if we decrease the density of particles and thereby the effective interaction strength between them, this kink shifts to the left. So it shifts towards the point of an Anderson insulator as we dilute the system. All right, so let's go to this final question of this finite thermal bath. So the question that we want to ask now is what happens if you mix a system which sees disorder with a system that does not see a disorder and has fully thermalizing evolution? Okay? What is going to happen to the total system? Is this one going to delocalize this one, or is this one going to localize this one, or can both of them persist in the experiment? Okay. The way we do this in the experiment is we tune our disorder lattice, the projected disorder potential, to a very special wavelength, such that the AC Stark shift, the light shift for one of the spin states is finite, but it's 0 for the other spin state. And this effectively means that this other spin state, this spin down state, does not see the disorder potential. Even though the light is there, it's like there's no polarizability, so it just does not see the disorder potential and evolves completely as without disorder. Interaction strengths are almost equal between all spin states for rubidium. And for this experiment, we prepare a charge density wave. So we take our mod insulator and we make this zebra out of it. So we chop it into slices, okay, where every second lane is missing again here, every second line is missing in this charge density wave, artificially prepared. Then we use kind of coherent Rabi rotations to kind of change the density of spin ups versus spin downs. So it's completely controllable how many spin ups and spin downs you have in the system. And then you let the system evolve. And then you see how this charge density wave evolves. So first let's look at the system without just one spin component. the one that sees the disorder. And there you can see indeed that the imbalance, even for very long times, this time up to 1,000 tunneling times, saturates at this finite value. Okay, so now we can say up to 1,000 tunneling times, we see this, we have evidence for this localization behavior in 2 dimensions for the true system. What we also see is if we keep adding this other spin component that does not see the disorder, so this is for delta equals 36J, that the more and more we add the other spin component, there's some point where we cannot localize the spin component anymore that sees the disorder. Okay, so there's around 30% fraction of these delocalizing particles where also the spin up component which sees the disorder would completely delocalize and imbalance would decay to 0. We can actually look at the 2 spin contributions separately. We can actually also look what the other spin is doing, the delocalizing spin induced doing, and that's interesting also. If you just have the delocalizing spin itself, you see that's very trivial. You start with a large imbalance, but immediately you go to 0 because you just spread out in the trap equally between even and odd sides. What is actually interesting, in the presence of the particles that are localized, you see you lock into a negative imbalance first, and this negative imbalance just comes from the fact that these delocalized particles, they see the random potential, but indirectly through the interactions with the localized particles, okay? Because they have this charge density wave set up. Through the interaction between them, they see a reversed potential and they lock into the opposite reversed potential, but eventually relax. Now here's the maybe, I think, most interesting plot and I think quite surprising result that we see so far. This is the delocalizing component, and this is the one that sees the disorder, and we look at the long time imbalance that we see in the system. And what you can see is that over a wide range of parameters, there seems to be a coexistence of a delocalized phase with the localized phase. Okay, so I think that's quite surprising, and that needs to be understood why that is. But if you go to very large kind of spin down fractions, delocalizing fractions, you also kill the localization phenomena in the spin up particles. Just as a final slide, let me add this. This just shows again how this transition point is shifted now upwards as you add delocalizing particles. So this is our transition point I showed you before. If we would dilute the system, we would go left. If we add these delocalizing thermal particles, this finite reservoir, we can still localize the component, but we need to go to a larger interaction strength. Now, whether that's true, whether that remains true for all possible percentages of these delocalized particles, that's an open question. Maybe there is a point, whereas you cannot, even for very large disorder strength, you cannot localize this other spin component even anymore because the thermal bath has just become too large, and that's an open question. All right, I think there are many open questions, but I think I'll just stop here and hope presented some interesting new results for you on this surprising results, at least for me, on this 2-dimensional systems and the coupling to a thermal bath. And with this nice picture of Munich, actually we're just around the corner here in this building. I just leave you and thank you very much for your attention.